So today we're going to discuss about identifying regions under the normal curve corresponding to different standard normal values. So yesterday we have discussed about how to compute for the mean and the variance, and now what we're going to do is to, of course, talk about how to properly identify the regions under the normal curve. So we have already have recalled what is a normal curve, and a normal curve is about how data are distributed normally that are actually using the mean as the highest point, and that the distance between data would be based on the standard deviations. And at the same time, we have known that a bell shape, it's bell shaped, and that it is actually symmetrical when half or cut into the middle using, or we try to separate the data using actually the mean. So now, these are the objectives we're going to use to guide us as we go on with the discussion. First, to describe a normal, standard normal distribution and its parameters. Second, is to compare and contrast standard normal distribution with the normal distribution. And lastly, to identify the regions of the normal curve or under the normal curve corresponding to different standard normal values. So take note, we're going to deal with standard normal values. So let's first define what is a normal distribution. So there are two parameters. We have the mean and the variance. And normal distribution is also known as a normal curve. So most of its observation are centered around the mean. And as you shifted beyond either side of the mean, there will be fewer data in the observation. So as we know, in the bell shaped, it actually is as we go farther from the center, farther to the left or farther from the right, it actually gets what they call it one. It actually gets thinner or smaller because the data are actually getting fewer. Then we also have the empirical rule, which states that within the first standard deviation, both from left and the right, it actually covers 68%, or the data, 68% of the data covers the first in within the standard deviation. Then if we are already moving to the second standard deviation from the left and the right, we already have 95% of the data covered. And lastly, if we are dealing with the three standard deviations of the mean, then we have 99.7% already. So that is what we actually have discussed before, and now we're just having simple recall about. So I hope you still can um, jog your memory so we can still recall that part. Now, let's move to the definition of the standard normal distribution. So, a standard normal distribution, or the is also known as the z distribution, is also a part of the normal distribution. But what we have here is that the mean would be equal to 0, while the standard deviation would be equal to 1. So these are our parameters, and it is useful to examine data and classify them through percentile ranking. So standard normal variate. So when we talk about standard normal distribution, we also have the standard normal variate, or the variation for the standard normal data. It will be denoted by z, and is a continuous random variable that follows a standard normal distribution. When we write it as z, is yan po yung itsura niya. Okay, next po tayo. And now let's talk about the characteristics of a standard normal distribution. So now take note, as I mentioned earlier, standard normal distribution is also symmetric. And as you can see, the x is also equal to the mean, and which is also equal to 0. So the mean is actually the middle number, and that is represented by 0. Then we have here asymptotic with respect to the x-axis. When we say asymptotic, the curve is actually getting closer to the x-axis, but it will never intersect or even meet with the x-axis. And lastly, that the total number of the total area rather of the standard normal curve is actually equal to 1. 50% is covered by the left side, and another 50% is covered by the left side of our mean. So 50-50. Now let's move to the characteristics still. So this is what I have made mention earlier, that they covers actually 68% within the first standard deviations, -1 and +1, while 95% of the observation in the population already it lies within the two standard deviation because we have here -2 and +2. And lastly, 99.7 would be lying on the -3 and third standard deviation. So that is how they actually covers, how they get bigger. The standard normal distribution shares the same characteristic with the normal. So it's a part of the standard normal, the normal distribution. That's why it shares the same characteristic. Now, so look at this one, the normal curve and the standard normal curve. So as you can see, the normal curve, it also has a, it's also bell shaped. But what's the difference between the two? As you can see how it is drawn, it's more bumpy, and the other one is a bit flat. And as you can see, the mean or the mu is equal to 5, while the standard deviation is zero point 0.2. So this is how it looks like on the graph on the left side. Well, on the right side, as we can see, the total error, the standard deviation is 1 and the mean is 0. So that's how they actually differ when it comes to their shape. Something, the right one is flatter, while the other one is a bit bulkier. So take note the total area for both normal and the standard normal curve is actually equal to 1, which represents probability. Now, for the normal curve and standard normal curve, graph 1 is a normal curve because it has the following variables. So as you can see, this is how it looks like. And as you can see, it's shaded because that is um, within 4.2 and 5.2. So for example, that is how the area you're looking for. While for the standard normal distribution, this is the shaded region for -1 to zero point 0.4. Ayan. So yun lang naman po. That's how different they were. So this is the interval, and also the same goes for region. The second image, there's also a shaded region, or the so-called um, the area under the normal curve, standard normal curve. Now, let's define the area. So area, or the region under the normal curve for any intervals of values of the normal random variable x, can be defined as proportion of the population with the characteristic described by the interval of values, and also the probability that randomly selected individual from the population will have the characteristic described by the interval of values. Now, so how do we do this? So to identify, what we need to do is number one, we'll identify first the parameters desired and the desired interval of values from which the area under the curve will be evaluated. And the second one, we're going to draw the normal curve and mark the region. And of course, to standardize the values of x to z-scores using the formula z is equal to x minus mu over the sigma, or x minus the mean over the standard deviation. Now, then afterwards, we're going to sketch the normal curve, mark the desired region by the z-score, and of course, we will be using the z-table that you can find in your Google Classroom to find the area of the standard normal curve. So the z-table summarizes the cumulative probability distribution for z. The table values represent the area to the left of the z-score. So as you can see here, this is the area covered. Nakikita nyo naman po itong table. So yan po. Kung makikita nyo or mahahanap nyo po yung binigay kong copy sa inyong Google Classroom, it would be easier for you to look at it and use it. I have already been able to give you the idea on how to use this one by looking for the on the leftmost part of the leftmost column and the topmost row of the table. Now, as you can see on the column that I was mentioning, the leftmost column covers or contains the whole number and the tenth place of the z-score, while on the first row of the table actually covers the hundredths place. So if you're going to look, for example, 3.41 or -3.41, you're going to look for -3.4 and then 0.01. And the area or the part of the table or the cell where they actually meet when you try to intersect them, then that is actually the value of the area covered with that z-score of -3.41. So for example, The height in centimeters of 110-year-old males in the city are approximately normal with the mean of 130 centimeters and the standard deviation of zero point 0.5. So what is the area under the normal curve between 1.29 and 130.4? So all we need to do is to actually solve for the z-score of both. So we have 129 and 130 using the value or the formula z is equal to x minus mu over the sigma. So take note that the x here, we have the 129 and we also have the mean 130 and the standard deviation of 5. So you simply subtract. So we have 129 first. 129 minus 130 is 1 divided by 5. That would be equal to 1 over 5, or in decimals that is negative zero point 0.2. So from 0 we'll be moving to the left to cover zero point 0.2. So we have here, as you can see in the um, illustration. And on the right, as you can see, we'll be using on this part, we have here, I'm sorry. On this part, we have the second z-score. So we have 130.4. We subtracted from 130 and divided by 5. So we'll have 0.08. So that would be on the right of 0. So negative zero point 0.2 and 0.08. So that is the area covered. Now, what we're going to do is to look for the areas covered using our table of values. And as we know the table of values, so we're going to have zero point 0.2 and zero point 0.8. So negative zero point 0.2 is actually 0.4207 and 0.08 is actually 0.5319. So 0.5319 actually is this one from this line to this. So that is 0.5319, while from this one to this side, that is the point 4, the value for ano, we have 0.4207. So to get this particularly small portion that is covered by them, we'll have to subtract them. So after subtracting them, we'll have 0.1112. So that's it, how to solve for the area or the region of a standard normal variable, or normal curve, I should say. Thank you, and please see your activity at the Google Classroom.